Today we are looking at unified framework for blast furnace telemetry and system optimization. Our goal is to move beyond simple observation and understand the complex mathematical relationship that govern coke consumption and productivity. In a modern blast furnace, every variable is connected. We cannot change one factor without affecting the other factors. So this presentation will provide uh, a methodological roadmap for calculating exactly how different parameters influence your furnace performance, allowing us to move from reactive troubleshooting to proactive systematic approach. To optimize effectively, we first have to admit where old method failed. Historically, legacy empirical diagnostic failed because they looked at variables in isolation. When you assess variables separately, you end up duplicating component effects and overestimating the impact of isolated changes. This leads to error in calculating absolute magnitude. Instead, our unified systematic approach combines analytical and empirical data. We look at three things: the absolute magnitude of a parameter, how it combined with other factors, and general level of process development. We are not just looking at numbers, we are looking at relationship between them. Now, to manage the furnace, we categorize our input into three pillars: batch factor, blast factor, and organizational factors. Batch factor include things like iron content and coke chemistry, while blast factor involve temperature, moisture, and oxygen enrichment. Organizational factors like pressure limits and downtime frequencies are often overlooked but are just as critical. So, all these variables feed into two primary KPI: coke consumption and productivity. Our systematic approach allows us to see how a small change in raw material strength can result in a specific measurable decrease in coke consumption or boost in output. So let's first look at a batch. So a key sight from our telemetry is that iron enrichment impact is non-linear. This means 1% increase in iron content doesn't always give you same result. For example, if your baseline is below 50%, a 1% increase yield a 1.4% coke reduction. But if your baseline is already 55 to 60%, that same 1% increase only give you a 1% reduction. Slag content follow a similar rule. A 10 kg per ton hot metal decrease reduces coke rate by 0.35% and boosts productivity by 0.6%. This takeaway is clear: the lower your starting iron content, the more sensitive your furnace is to variation. Now, coke is the backbone of the furnace, and and its physical strength and wear susceptibility drastically alter the thermal balance. A 1% increase in coke strength yield a 1.5% reduction in consumption, while a 1% decrease in wear susceptibility MICAM 10 value can boost productivity by 2.8%. We also see a massive sulfur nonlinearity, reducing sulfur from a 0.05% baseline only cuts coke by 0.18%, but reducing it from a 0.01% baseline cut it by 0.71%, a 4 times amplification in impact. This shows that as you reach higher level of purity, a small improvement becomes even more powerful. So when we substitute the solid coke with uh, other fuels, so so we must use an equivalency scale. However, this is a a major difference between theory and reality. While 1 kg of fuel oil might theoretically replace 1.2 kg of coke, engineering data shows that practical equivalencies for the natural gas and coal are actually 15 to 20% lower than the theoretical limits. This is due to incomplete combustion and soot liberation in the furnace. To optimize, we must balance this stream, that is natural gas, pulverized coal and coke oven gas, against the equilibrium of solid coke bed to maintain the process stability. Now, every furnace has a speed limit, the limiting gas pressure difference. So, forcing smelting can increase productivity, but if you exceed these limits, coke consumption will skyrocket and productivity growth will stall. So, these limits are strictly tied to furnace volume. A 1000 cubic meter furnace has a 130 kPa limit, while a 5000 cubic meter furnace can handle 1.80 kPa. We use the formula, that is delta P, which is 450 divided by coke consumption K, to find the threshold, and pushing beyond this limit creates turbulence that destroy the efficiency of entire system. So, a striking point for every operator to remember is that process stability is often more important than the baseline chemistry. True optimization requires minimizing fluctuations or standard deviations. By simply eliminating batch inconsistency like dosing error or moisture fluctuation, you can yield up to a half% gain in productivity without ever changing your raw material chemistry. For example, reducing blast moisture fluctuation by just 1%, 0.1% rather, can cut coke consumption by 0.45%. Stability is not just about good material, it's about consistent material. So why cannot we just keep adding improvements forever? Because of damping principle. As we move closer to an ideal state, the effectiveness of every new measure mathematically decays towards zero. To overcome this, we use combination principle. This requires introducing opposing measures that can act in different direction on furnace processes. So when you combine this correctly, you reach a synergy point where the net efficiency boost is far higher than if you had simply added the measures together. Optimization is about balance, not just addition. So finally, we reach the principle of limiting states. The blast furnace is a unified macro system. As technology improves and we move toward a limiting state, the effectiveness of further measure will be categorically decline. The final law of optimization is this: it is not about seeking infinite linear gains. Instead, it is about managing system entropy to hover precisely at threshold of limiting state. By using the data and threshold we have discussed today, we can keep our furnace operating at that peak edge of maximum productivity and minimum fuel rate consumption.